So welcome to today's 51st TMS Tuesday, another major landmark. Today we have Tony Smith, eminent expert on airfield lighting, developed a lot of the standards as we know, inventor of the PAPI. Will today share his vast knowledge and experience of low visibility operations. As you know, low visibility procedures exist to support low visibility operations. We're very familiar with those low visibility procedures, but what exactly are low visibility operations, and what actions do we take to support them? And today, to share more light on this area, Tony Smith is going to share his knowledge. The webinar team today is Tony, of course, will be making the presentation. Kevin and Tony from TMS Training, experts in airfield lighting training, are on the panel today to answer your questions. Please use the chat box to log your questions so as we don't interrupt the flow of Tony's presentation today. So just type your questions in the chat box and we will try answer as many as possible live today. Carl Johnson is joining us from United States of America, from Florida, I believe. Carl? I think Carl is in Florida today.
Yep, that's correct.
The sun is shining, I hope.
Yes,
and myself from Tailor Made Systems Marms. So welcome to you all. I don't believe Seward has joined us yet today. Hopefully he'll join us later for the Q&A session.
Yes, I'm here.
Oh, Seward, sorry, I missed seeing you.
Goodness.
I missed you. So welcome, Seward Ford, independent specialist consultant with a lifetime of knowledge of airfield lighting. Firstly with Kraus Heinz, then as a AAAE airfield light trainer, responsible for the ACE training course, along with his partner in crime, David Rainey, and working on an independent consultant, working on a lot of projects, including LED development. So without any further ado, low visibility operations. I'll hand over to you, Tony.
Good afternoon in the UK, and good whatever it is, morning, noon or night, wherever you are. It's a privilege to make this presentation, be asked to talk really from my experience of low visibility operations. Just to say, perhaps as in the introduction, why me? Well, I've been associated with providing visual aids and aids for pilots taking off and landing virtually the whole of my research career. The first part of it, it was actually more to do with operating aircraft off aircraft carriers, but it was all to do with making landings in particular safer and more regular. And in 1970, I actually moved from one lab to another within the RAE into what was called the Blind Landing Experimental Unit, which I think explains what it did. It was set up specifically to work the subject of low visibility operations, leading eventually to zero landings. That was what it was set up for. Bearing in mind in the mid-1940s, when civil aviation really was winding up, there was an awful lot of accidents during landings in low visibility. So that was the environment I came into, and I've had a lot of experience in various ways, but largely to do with the visual landing aids that are subjects today. Well, low visibility operations, I said it's a big subject, so I tried to write down a definition that I'll try and work to today. It's about taking off and landing aircraft where the naturally occurring visual cues do need to be augmented by visual aids. And in that, there's a good point to make that any visual aids you add to what's already there shouldn't be such that the pilot has to do something abnormal. He should be able to land control and land his aeroplane in the same way as he's done before and as he's been taught to do. He shouldn't have to learn the new aid. The realities of low visibility operations briefly are when you try and talk about providing visual aids, it's for many of them, it's the lowest visibility that defines the lighting specification. Now, this is important. A lot of people will see these visual aids, but even in operations, may never see them in use in the lowest visibilities. And so they may think, well, as long as there's some light coming out of it, that's sufficient. You've got to remember the requirement is that you've got adequate cues for the lowest visibility, and that generally means highest intensities and well-defined beam spreads. There are, when I was doing landings in low visibility, there is a need that the visual aids have to be augmented by non-visual guidance and control information. This isn't just to augment what the pilot can achieve when he is visual with the visual aids, but often to lead the aircraft into the position where he can start to use the visual aids. In other words, join the approach to a runway when the runway isn't actually in sight, and on these non-visual guidance in some form or other to put the aircraft there. I haven't addressed a whole lot of things, including ground movements, and that of course includes taxiway lighting and signage and many other things. But some of the constraints in what we provide, that applies right across the board and will apply also to things like helicopter operations, which I shan't touch upon today, although I've done quite a lot of work in that area. Let's move on to the next slide then. That's worth going back, a very quick, sketchy overview of earlier history of visual landing aids. If you read the books, you'll find that back in the 1910s, the flight operations were limited in practice to clear daytime conditions, and that, of course, was very inconvenient and indeed dangerous situation. But that you had to be in touch, visual contact, good visual contact with the ground in daytime conditions. Going from A to B, you were using a map and what you could see on the ground. So it was, all landings were done in clear daytime conditions only. Well, then, as aircraft developed and the early development of airlines came along, there was a need. People were crying out to say, well, I can only land when I can see the ground well lit by the sun. Can we turn night into day by using floodlighting? And in fact, there's the well-known story of Lindbergh arriving at Paris in 1924, I think it was, and the landing area was illuminated by a whole lot of people with their cars shining their headlights onto the grass strip that he landed on. That was an attempt to turn night into day, and quite an undertaking if you think about it. But that was the first response, as it was, to visual landing aids. By the time we got to the 1940s, there were simple runway lighting patterns emerging, particularly when we got to concrete or tarmac or whatever roads, and not just landing on the grass into the prevailing wind. Lighting patterns emerged, and that was facilitated by an increased application of electrical circuits out on the airfield, so you could have lighting patterns with a lot of lights. You could just switch them on. You didn't have to. Some of the earlier things, of course, were flare paths. They literally were paraffin lamp, and you had to light each one and put them in place. So being able to have the lights permanently installed and have electricity providing the light was a real step forward. But the lighting patterns, many of them were, well, I think it would work. This would work well, and we'll try that. Some were, when you look back, were not too bad. Some were pretty awful, actually. By the time we got to the 1970s and 1980s, it was becoming clear that the visual landing aids that had been developed had suboptimal performance. And we did find cases in our research. As a result of an accident, we showed that the lighting aids that were then agreed pretty much internationally actually could induce landing accidents. They were not fit for purpose fully. They were a big improvement on not having anything, but they really weren't fully fit for purpose. So that's the early history, and as I say, very, very compressed early history. So if we go on to the next slide, looking at it in a slightly different way, how did the lighting of visual landing aids develop? Well, in the 20s and 40s, I think it's fair to say the main effort by the lighting manufacturers was to provide high-intensity beacons. You could say this isn't a landing aid. It certainly isn't. But it's certainly an approach aid, finding the aerodrome in marginal visibilities and at night isn't necessarily an easy task. And so these high-intensity beacons were developed. In the UK, there was a light called a chance light, and that was reported that on a good night, when the visibility was quite reasonable, as you were flying from Paris to London, you could see the chance light at the London airport whilst you're over the English Channel. They were big bright lights, and that was where a lot of engineering was going on at that time. And in fact, and Seward might want to comment on this, the first airways across the United States had high-intensity beacons every few miles, so the pilots could fly from one beacon to the next, right across the United States. In the period of the 1940s and 1960s, certainly in the UK, there's a realization that if civil aviation and the military were really going to be all weather, they had to do an awful lot of work to be able to achieve this, both improving technologies and also understanding what was going on. This is why the Blind Landing Experimental Unit in the UK was formed in 1945, I think it was, with the objective of eventually being able to have the visual aids and the non-visual aids, a total system that would enable you to have a 0-0 landing. The pilot wouldn't see anything until he literally was taxiing along the runway. In preparing this, I was looking through documents, and I found a document written by Calvert in 1945 as a sort of resume of what was understood and what was still a mystery about how you provided adequate visual aids. It's quite interesting to read, and a lot of things that he says in there were indeed real problems and took quite a lot of sorting out. But I keep mentioning Calvert because he was one of the leads. There were people in the States who he was working with, in particular in France and some degree in the Netherlands. But Calvert, I think, made the big breakthrough because he said we've got to properly understand, before we develop the lighting any further, we've got to understand how a pilot uses a lighting pattern to control the aircraft during the approach and landing. You could get as many opinions from pilots as there were pilots, and perhaps a few more. But how does it actually work? And he lighted upon the idea of drawing perspectives of what the runway would look like, or the taxiway, the runway edge lighting, threshold lighting, and approach lighting, what it would look like at various positions on the approach and during the landing, both when you're on the center line and when you're displaced to left or right or high or low. and then you could work out from that things that were going on as the patterns changed in shape and size as the approach was continued. And this was all very solid work that led to an agreement pretty much what the lighting patterns should be. And that work was actually very foundational and really turned the development of the provision of visual landing aids, I think, into a profession. I think before that it was still very much a cut and try and see if this works sort of world. But the theoretical world in that period did a lot to help us all understand how, if you're asked for a visual lighting aids suite of lighting, what do I have to provide, and how do I have to provide, and what motivates what the patterns are. Well, in 1961, then ICAO was establishing a visual aids panel to promote international standards. Clearly, let me just kill that. Sorry about that. In 1961, it became clear that as flying was becoming more and more international, it was important that the standards were the same. So wherever a pilot would go, he would get the same visual cues provided. And that panel started work in 1961, chaired by someone that certainly Seward knew, and others, Carl presumably, Charlie Douglas from the United States. And he was a real guru in this, and he'd been involved in various activities since the 1940s. And he was a really excellent and very knowledgeable chairman of that visual aids panel. And he was still chairman of it when I first go away. But that you can't underestimate the value of that visual aids panel, because it didn't just write the rules and regulations. It's actually encouraged research and sharing of research insights across the nations. A very stimulating place to work in the 70s and 80s, I found. But when we got to the 1970s, I began to realise in the UK, possibly more so because we had a nasty accident in 1969, where an aircraft on approach actually nosedived, is the only way I can describe it, into the runway and into a terminal building at Heathrow. And that set up a government-sponsored big research program to try and find out why it happened and what could be done to improve the situation. And it was in that period that we began to realise that we really didn't understand the nature of fog. A lot of assumptions that if you knew what the visibility was at ground level, then when you're on the approach, you'd have the same visibility. We found out that wasn't true. And I'll say a little bit more about that in a moment. Fog has particular characteristics. They're variable from day to day. Within that work in the visual aids panel, we did work because of what we were finding about the fog and so on, that we would introduce a greater vertical beam spread, in particular, to certainly improve operational safety. Often pilots reported a black hole in the approach, that they saw some lighting, then it disappeared, and then it came back again. And that was being attributed to the characteristic of the fog. We found that it wasn't a characteristic of the fog, it was a characteristic of the lighting. It wasn't adequately matched to what's actually needed. So whereas in the the 40s to 60s, we were looking at patterns. In the 70s and 80s, we were looking at beam spreads and setting angles and intensities. As part of this work, in my research group, I had a guy who was a whiz at making computer models, and he made computer models based on a lot of research into fog, how it varies with its density, varies with height, data he got from a mast, which we erected, and he did an awful measurement of lighting performance, which he then found there were other people who had done similar work and got some of the same answers. So we thought that was a pretty good model. And not only did we think from our research studies it was good, we actually were able to mount fog trials, actually go flying in fog and show how this computer model, in fact, making the measurements vertically of the fog, not just the RVR, we could actually predict the first contact height on approaches in fog to an accuracy of about 3%. In other words, we would say you'll get contact at 153 feet, and the pilot would actually get at 150 feet. That was a big standard improvement. Personally, I think it's a great pity that ICAO and others didn't take up the idea of monitoring the vertical profile of the fog rather than just the RVR at ground level. We would have had greater safety and more regularity of operations. But there again, that's another day in more detail, perhaps. So let's go on to the next slide, if I may. What that fog modeling showed that most fogs that we operate in, there is a formation phase, but for most of the time when we're operating in fog, we're operating from an attenuation situation that extends from the ground to a fog top, a fairly well-defined fog top, with good visibility above it, and also but the fog extending down to the ground. And what the research showed that each fog, any day you measured the fog, you could measure the density of the fog with height, and you would always find that the most dense fog was at the top of the fog, just below the fog top. That's where the density is greatest. And then as you descend, the density reduces, and so the distance you can see ahead increases until when you get on the ground, the distance ahead you can see is what is reported as the RVR. But at heights above RVR, you're not going to see what you see in terms of seeing distance ahead that the RVR reports. So RVR is actually a poor indication of what we'll be seeing from approach to approach, from one day to another. Same RVR, you'll get a very different sequence of what the pilot sees when he gets contact and what happens thereon. We have to recognize that variable fog sequences are inevitable when you use RVR as the main means of controlling. You're going to get occasions when you generate overshoots and other occasions when the pilot sees lighting well in advance before the decision height. And this variability in fog density gradients results in that spread of landing success rates that you probably know all about. This is there's an overshoot percentage attached to a given decision height RVR. That's coping for the variability, and the decision height that is chosen is one where most of the time, over a long period, if you like, you make all the measurements, you'll get a high probability of a landing decision being made when the pilot is having to make a decision whether to proceed. If you take that RVR. If you go for a lower RVR or higher RVR, you get different results. So that was the fog model, very powerful, and you can use it backwards, as it were, if you know you're asked for a lighting pattern. You can use the fog model and work backwards and actually determine what lighting pattern and what intensity is needed to produce a given level of landing success rate. Very powerful tool. So if we go on from that slide to the next one, please. Now here's just it's just a busy slide, and I don't spend too long on it. But what I want you to see is that we've got height on the vertical axis and the slant range, in other words, the distance ahead, if you like, the pilot can see at any given height. So if you go near the top, you'll see it says RVR times 100. And that, in fact, if you follow that line down to where it says threshold, you see that the first contact light at 3,000 feet, you're making contact in this fog, this particular fog, you're making contact at a height of about 84 meters with the first light, and then you see others as you come down till you get to where it says threshold light. When you've got to there, that's when you transfer from approach lighting to runway lighting. The line then goes diagonally to the left a little way, and then you hit the runway lighting. And so if you follow that one down, you'll find it finishes up on the ground at 800 meters RVR. You'll see I've noted that there at the bottom. So there's an 800 meter RVR where the pilot would get initial contact at a height of 84 feet, and the slant visual range, looking at the ground, we'd see something like 340 meters. And anything to the left of that hatch line is, although the lighting might be there, you won't be able to see it because it's below the cockpit nose cut off. But you can see, I think, as the RVR comes down, so the initial contact, it's by the time at 700 meters, you'll just about get contact at 300 at the first approach light. If you come down to the other end of the side of the diagram, let's take the 200 meter case. You see, you won't see any lighting. If you come down there, that one there, 200, you'll see that you won't get any lighting until you're down to 1,000 feet, and you'll see it at the cockpit combing. So in very low visibilities, you know always you'll see the first light at the cockpit combing. In the longer visibility, the 800 meters one here, it's way out beyond the cockpit cut off. You'll see the first lights. But this shows you the dynamic range as the RVR varies, where you get visual contact. Now, I've got, that's one particular fog. It's a fog which statistically, from all our measurements, you would encounter over the years, you would encounter a fog of this characteristic or worse about 10% of the time of your operations. 90% of the time, it will be better than this. So if we look at the next slide, this is just an example of, in fact, 3 of these different ones. You see the one on the left is the one I've been talking about. The one on the right is where you get 50% of the time. It will be better than this. You know, that's a very fairly easy to operate in fog. The one in the middle is somewhere in between. So you've got something like the left-hand one is 10%. The one in the middle is 2.5%, and the one on the right is 50% probability. So you see that there's a large variation, but we're able to monitor that, and we understood by the 1980s how it all worked. So go on from there, if I may, to the next slide. And I think this is a little fog, so we just pause it just for a minute. So I wanted to say this is very old film from the line landing unit. The sound isn't very good, but that doesn't matter, I'll put to you, because this was taken in the days when we sorted the patterns out, but we still hadn't sorted the approach lighting and runway lighting specifications properly. So you'll see some of these cases where you get a black hole in the approach. You see some lighting on the approach, then you don't see anything, and then you see some runway lighting. And the commentary, knowing what they did at the time, attributes this to the fog. And in fact, a lot of that was due, in fact, to the inadequate lighting specification, particularly the lack of adequate vertical beam spread. So if we look at this, as I say, it is old film, but I thought it's worth showing just to, for those of you who never actually sat up front and seen a low visibility landing, see the sort of thing the pilot is coping with. So let's look at this now.
Approaches and landings in low visibility. By day. Initial contact height, 310 feet. Runway visual range, 1,000 meters. IKO Category 1, low visibility conditions. The pilot is using manual control for the approach and landing. The lower limit of Category 1 is internationally accepted as the operational minimum for simplex flight director or autopilot approaches using barometric height. Visual contact. The pilot now has about 12 seconds to make any lateral correction before starting to flare. The number indicates the height of the aircraft in feet, measured by the radio altimeter. Initial contact height, 60 feet. Runway visual range, 200 meters. Category 3 with decision height. Conditions are even worse. Although a large number of manual landings have been safely achieved in RVRs down to 150 meters at RAE Bedford, the pilot must generally rely on fully automatic approach and landing systems and specific crew procedures. Airlines in the UK have been cleared for operations down to minima of 50 feet and 250 meters, using failed passive airborne systems and Category 2 ILS ground stations, and further reductions are being considered. A glimpse of the final approach lights is obtained, but the first useful visual contact is with the white painted threshold markings. Markings are generally more useful than lights in daytime fogs. Category 3B, corresponding to a minimum visual range of 50 meters. Another fully automatic approach and landing. For civil aircraft to be able to operate regularly and safely in such conditions, fully automatic approach and landing systems are essential, in which a single failure does not affect any aspect of performance. Such high-integrity fail operational systems currently equip a large number of modern aircraft from delivery and are an accepted requirement for international scheduled airlines. Approaches and landings in low visibility by night. Category 1, and an approach in shallow, patchy fog at night. These conditions occur during the formation period of the fog. The visual segment, the length of the lighting bounded by the cockpit cutoff, and the most distant light visible to the pilot, is large. About 1,050 meters at a wheel height of 280 feet. Visual segments are generally longer at night for the same fog conditions. Category 3B, runway visual range 150 meters. In such conditions of shallow and patchy fog, the pilot can make visual contact early in the approach, and he could assume he would have a large visual segment to touchdown, but for the reported RVR. 4 crossbars are still visible at a wheel height of 250 feet. As the aircraft approaches the fog tops, however, the visual segment shortens, and at 150 feet, there is barely 150 meters of approach lighting visible. Category 3B, runway visual range, again 150 meters. On this approach, the fog is deeper, and because of this, the visual sequence experienced by the pilot is different. The first visual contact is established at 170 feet. But only brief glimpses of the lights are possible down to 70 feet. Contact is momentarily lost until the runway lights are again visible at 40 feet. The remaining 2 approaches highlight conditions of shallow, patchy fog and deeper fog for a visual range of 90 meters. Again, after earlier visual contacts, the visual segment shrinks and disappears. Contact is not really established until the aircraft crosses the threshold. Runway visual range, 90 meters. Near the lower limit of Category 3B, and with conditions of deeper fog. This filmed sequence of approaches in various low visibility conditions enables pilots to experience the changing visual sequences associated with different fog conditions.
Well, there we are. I wanted to include that bit of film because it's interesting. It just gives you some feel for what pilots actually see, how little time they have, and how they must see the lighting patterns if they're going to make a decision to manually land the aeroplane or allow the approach to continue. It's good for that point of view, but in fact, I would, if I was going to use that film much, I would change the commentary quite considerably, because that film was made before we understood about fog gradients, and there's a lot of comment in there about low visibility and shallow fogs. That was a real concern at the time. This shortening of the visual segment as you proceeded, in fact losing the whole thing. Some of that was due to the shallow fog because, to put it bluntly, don't make a decision to manually land above the fog top, because if what you see there is not what you'll see on the way that when you enter the fog, you'll get a big reduction in what you can see, and then it will gradually open out. At the other extreme, Category 1 operations, when we have pilots involved in discussions on this, you'll get the align party. Our company operates to Cat 1 minimums, and we really don't need any of this lighting because we've got an autopilot and so on. First of all, with a 200-foot decision height and 650-meter RVR, the chances are they may have been flying the line for years, but have never actually operated on the actual minimum. Just because you've got a clearance to operate there doesn't mean to say you've got a lot of actually practical experience. So don't be put off when pilots say, "Oh, I don't care about the lights, they don't play an important part." They do when the push comes to shove, when it really matters. But ICAO in the period in the 60s came up with these three categories of operation, all requiring more and more aids, both non-visual and visual. Category 1 these days is 200-foot decision height and an RVR of 650 meters. I think that's still right. It was a few years ago. Category 2, the decision height you can come down to is lower. The minimum RVR you can operate in is 350 meters. Then this Category 3, A, B, and C, where more and more the pilot is relying on the autos to fly the airplane. And certainly when you get to Category 3C, the whole operation, until you feel the bump on the ground and the main wheels and the nose wheel are running, you may see absolutely nothing out of the cockpit. And so the visual aids don't play a great deal in Category 3, except, of course, once you are on the ground, you need to see a minimum number of lights to make sure the aircraft is still traveling along the center line, and also to see where the taxiway lighting comes in, so you can take where you're going to clear the runway, the access onto the taxiway, the rapid exit taxiways. So even in Category 3, there are places where visual landing aids or low visibility lighting is important. As I say, isn't time today to talk about that, but that's very important in the taxiways. You require fewer lights for Category 1 than Category 2 and 3. That's where it's essential in the 2 and 3 conditions to have a centre line and the touchdown zone lighting to enable the pilot to get enough visual cues to flare the aeroplane and stay tracking down the runway. And just that last point, in Category 1 and 2, these days, many of those conditions, the pilots in control will actually declare an auto land and let the automatic pilot land the aeroplane. But there is a requirement that in Category 1 and 2, there must be sufficient visual cues for the pilot to be able to land manually using the reference to the visual landing aids, not relying on non-visual guidance. So that's an important one. That's where you start to really rely an awful lot on the visual landing aids for safe operations. So that is it's a quick sketch of basically what happens as you go into low visibility procedures at your airport. So we just go on from there. I say that the precision approach landing is highly structured and based on an awful lot of research in all sorts of areas. And it is what you find in the Annex 14 and other annexes is actually international law. And if you're going to support precision approach landings, you have to provide all the components that make up the precision approach to have the required level of safety and regularity. And I just picked out some main components, and you may think there are others I've missed out, but I've just chosen a few just to show what we're talking about. Of course, one of the main components of the operation is the aircraft itself. The aircraft must be suitably equipped and be capable of operated in these conditions. And that will include things then like an automatic pilot for Category 3 approaches and landings, but also an automatic pilot for the non-visual part of a Category 1 and Category 2. There has to be an automatic pilot for you to operate these precision approaches. You can operate non-precision approaches using the lighting patterns, but that will require a much higher decision height and higher visual range requirements to operate. But precision approaches, where you're talking about essentially an ILS approach followed by a visual landing, or at least reference to visual landing aids. We come to the fourth of my bullet points, and that's the ILS, very precise non-visual guidance system. It took many, many years to get to the required level of safety and repeatability. Modern ILSs are quite a bit removed in performance from when I started taking part in this fog flying and sitting up front with the pilots and seeing what you saw on the video. The ILSs have improved, and they, of course, are absolutely core to getting really good low visibility operations. But the future, of course, holds almost certainly, and ICAO is talking this very much using ILS-based non-visual guidance rather than something that has aerials on the ground. And then the last one I've pointed out is our area, which is visual landing aids. They are specified by ICAO. They are all parts of the system, and they have to meet specifications. The first three of them are related to the aircraft. The fourth has components, obviously, in the airplane, the aerial, and goes with that. But there's also very much a part of it on the ground, the aerials, for guide slope and for lateral guidance. Whereas the one that interests us particularly, the visual landing aids, they're solely ground-based, and there's no doubt about who's responsible for them. It is the aerodrome operator, the person who holds the license for that aerodrome, is responsible for making sure this component is available when operations are taking place. So if we go on to, let's just look at those from an essential maintenance point of view, because as TMS says in relation to demands, you have to have a good means of monitoring what's going on, and then a good maintenance schedule to ensure that you meet the requirements. So if we look at those 5 areas I've chosen, let's look at the aircraft. What are the mandatory maintenance procedures that occur that you have to comply with as an airline and with operators? All aircraft will have a comprehensive time-based check and service schedule, levels 1, 2, and 3. It's all laid down, and the aircraft has to go through those checks and serviced from some services at every takeoff, every landing, therefore has had a servicing level applied to it. And of course, there are the deep checks, which happen a monthly or longer basis, but all written down and complied with without without any query. That is what you have to do. If you're going to operate the airplane, you have to have that maintenance procedure in place and demonstrably in place. If we go to the autopilot, which in a way is very much tied up with the aircraft itself, this will be part of the aircraft checks at all levels of checking, and particularly in the pre-flight, the pilot will check that his autopilot is serviceable, and if not, any faults or any problems are reported, and maintenance will be applied at the earliest opportunity. It may be that the flight is delayed because the autopilot needs to be serviced there and then. But you see, again, very much a very safety orientated procedure. Lots and lots of checks, and then appropriate maintenance as required. And then, you know, you may say, well, the pilot. Yes, the pilot is very important in all of this. He's one of the components. And I don't know how many people realise, but that man or woman at the front who's driving the aeroplane has had to have mandatory health checks fairly regularly, perhaps every 6 months or so, to make sure that they're healthy and don't have a condition that will make them being in charge of the flight a problem. So mandatory health checks of the pilot, we can say this is one component, which is checked for health, but also in terms of are you capable of doing the job? Regularly competency checks in flight and in simulators, overview by checking pilots and by simulator check pilots, making sure the pilot is using all the right procedures, using all the right equipment, making the right decisions. And so you've got a pilot who is very competent and very healthy and well able to do his job or her job. And if we go to the ILS, then again, here is essential maintenance, checking. Flight calibration is a component that in some ILSs that you'll have to have a regular flight calibration. In fact, all of them, I suspect, not totally sure where they are these days, but certainly when I was around operation, as it were, they have a flight check by the regulatory authority, but the ILS is operating within its specified limits and performance. And for category 2 and 3, if you're operating ILS there, then you have monitor facilities in the approach, monitoring the signals are where they should be. They're within limits. There are limits. There isn't an absolute zero. ILS, for example, you still get, let's say, for a category 1, the ILS, the azimuth can be 13 minutes of arc displaced from the ideal 3 degrees on the glide slope. It still just falls within the specification, but there are clear specifications, and if you haven't got your monitoring, far-field monitoring in operation, then an airfield can only operate to category 1 limits, even though it's normally capable of category 2. Very carefully controlled, very carefully monitored, calibrated, and of course service where necessary. And then we come on to visual aids. I think it's a very sad state of affairs. I can't write in there under mandatory maintenance procedures something where I can say this is what happens anywhere where precision approach landings are happening. We know very well from feedback from MARMS operations, in many cases, the mandatory performance is not being provided. Now, if you're a lawyer, what do you say to that? This is an essential part of the operation. It is mandatory that you provide it. So where is your mandatory maintenance procedure, which of course requires monitoring and then a maintenance program? Some airports are very good at this, but there are too many who don't. And as I was saying to somebody earlier, if you look at those components there, if you're using an airline, you'll never think for a moment, oh, these visual aids at this airport were installed 10 years ago, but they don't do any real maintenance. They don't say it's important. They bought the equipment, so the accountants think you bought it 10 years ago. It's actually still a light. I can still see light coming out of it. Oh, you don't need any money for maintenance. How would it be if you said that about the aircraft? If the airline said, we bought this airplane 10 years ago, the manufacturer said it's a lovely airplane. No, we don't do any maintenance on it. Would you want to fly with them? I'll let you make your own answer to that question. So let's just get down to the end now of this presentation. But another slide to go, just to show how the difference in approach lighting there, and where it's well maintained and where it's poorly maintained. There are gaps in it. You can see the center line there. There's gaps in the pattern. So let's go on to the next one. So I'm preaching a message that you have to be, with your visual landing aids, you have to be compliant with Annex 14 or its equivalents in your state. And there are benefits to it. Well, how do we do this? Well, I put it right at the top of that, train your staff. This is precision stuff, and it includes the visual aids. It is high tech, although we all have lights scattered around our houses and everything. We all know how lighting works, don't we? But VLA is rather more than that. So you need to train your staff, I think, to get any hope of having compliance. I could tell you horror stories of talking to maintenance people who really got no idea why they're doing what they're doing. And to do this, you need to make in-field measurements on a regular basis. And the frequency which you need to do that will depend on your aerodrome, both the ambient conditions, the number of movements you have, and so on. But you need to have within your documentation, if you like, something that says how often you will do this maintenance, when you'll do the tests and carry out that schedule. And then from that data, in addition to showing your inspector, as it were, that you are complying, you'll achieve this by developing maintenance schedules that respond to that on-field data, so that you do indeed meet the specifications. So why bother to do it? If I can get away without spending the money, says your accountant, the lights, I can see them when I drive around at night. What's wrong with them? You don't need to spend much money on this. Well, the benefits are quite important. First of all, it's a matter of compliance and meet legal requirements and avoid safety issues. If anybody had still got any of that lighting that was installed in the 1960s in their airport, they wouldn't be compliant because of the vertical beam spread requirements. They wouldn't be compliant. So the equipment has to be currently up to the current standards. And then you can be legal, but you must be legal actually. And won't be tired if something happens and you meet a lawyer and it isn't compliant. I'm very personally, I would say when there's any incident on a landing, there should be automatic first call of the people that are going to investigate the accident. The first thing they should do, the first thing they should do is actually call for for a check on the lighting to see that it's actually up to standard. And actually, we found as the development of arms went on, the airports that TMS were actually, they reported, perhaps a little bit to their surprise, that all this focus on maintenance was actually reducing their maintenance costs. It wasn't increasing. If you do the maintenance correctly, you actually reduce your costs. And of course, operation, you increase runway availability if you're compliant, and if you use good test equipment, you don't need access for such a long period to check or know which lights need to be cleaned. So there's some really significant benefits. So with that, I think it's time to draw this to a close. I hope you found it interesting. I've left a lot of gaps. I know there's so many things perhaps you want to talk about in more detail, but I hope that is interesting anyway, and gives some insight into why lighting VLA are so important and why it's important that they're properly monitored and maintained.
Well, thank you so much, Tony, for that insight. With your career, as you explained, having lived the development of the low visibility procedures and the visual aids to support low visibility operations, you know, it's you know, we know you've developed the standards, but it's so important that we understand why they've been developed and what they are, and why they need to be maintained. There's a great deal to be taken away from all of us there. So we've got our panel with us now, and we've got a couple of questions. Yana has asked us, can we get a copy of the presentation? Well, the presentation will be posted on our website, so you can see it on our website. It'll be within 24 hours of the finish, won't it, Damon? Would you say?
That's 24 hours. Yes, that's right.
Yeah. So within 24 hours, you can see the presentation on our website. Please inform. I've got a question here, which I'm just looking for. Low visibility takeoff, runway takeoff operations, taxiway centerline lights on all taxiways are mandatory. Few taxiways can be exempted with taxiway edge lighting. I'm not sure quite what the question is there.
I would interpret that, of course, if you go back into history, taxiways were illuminated by blue taxiway edge lights. Only the low intensity taxiway edge lights were blue. And if you had gone on to Heathrow back in 1960, when that was the standard, you would have seen what you could only do was described as the sea of blue. When you're sitting in the cockpit of the aircraft, you just see the whole aircraft aerodrome circuit covered with blue lights. It was very difficult actually to discern in junctions sometimes where you were going to leave the taxiway you were currently on and go off in a direction. There are lots of cases like that. And it just became obvious that to get good, reliable operations safer, I had to have centerline taxiway lighting. And I think it's fair to say the UK pioneered this very much at Heathrow. Calvert of honoured memory was very responsible, and he saw the ground movement as being rather like a marshalling yard in the railways, where you had blocks, you moved the wagons around and you marshal them together, and you used a guidance system, which is these blocks of green lights on the centre line, which the pilot then followed. And so they were switched, and there was a man in the control tower, in the visual tower, actually interpreting what the controller was telling the pilot to do, which taxiways to use. So and he was switching the appropriate lighting on and off. That can be done automatically these days and is available to do. But, you know, that's how you often start with a manual system. But taxiway lighting, if you haven't got the adequate taxiway lighting, you can do all the wonderful things on the runway, but if the aircraft can't get on and off expeditiously, you severely impede your operations.
Tony, in your career, you've had you've through the golden years of aviation almost. I think you had access to, for your scientific research, you had full access to a runway and pilots and aeroplanes, working very closely with national and international bodies. Where are we now with research and development into visual aids, would you say?
I'm not sure I'm competent to actually comment. I can only see from a distance. I suspect the FAA has some capability, but I don't think any other nation has at all now. And I don't know how much the FAA have. I think, you see, the reality is, whilst I said we did a lot of work in the 1980s to optimize the lighting approach and runway lighting, things have moved on. There's different lighting sources. From what we know about fog profiles and so on, we could actually tear the design up and redesign the lighting, I think, more effectively. We could, for example, I did some work which was reported in ICAO and in fact is reflected in our sort of reducing the number of lights and the pattern. Now, you know, considerably, like the touchdown zone lighting, the number of lights that are required to make the pattern up. And in fact, the centerline light spacings, the more extreme, very short distances that are required. We showed by both by studies, by extensive use of simulated, and also by actual flight trials, that you don't need, you know, 15-meter spacing or anything like you. And what you can cope with if you have light outages, we did a lot of work on that, and I did write a report which is available on reduced lighting patterns. So that reduces both the energy you use, but also, of course, the cost of implementing, going for, say, if you've got a category run one runway, and you've got to have a fairly large uplift compared to category 2 and 3, the number of lights you actually need is less, with one proviso, and it's very important in the context of TMS and so on. This procedure can be implemented, but the licensing authority must be assured that the lighting meets the specifications. So you can only go for this reduced cost, both of installation and operation, if you maintain what you have got, the required standards.
So, as you said earlier, Tony, the lighting must be compliant. So, what about Carl and Seward? What do you think? Do you think the FAA is vested in the testing to support the development of standards? Is that still going on?
They're working on standards. They're trying to update them. Their staff is limited at the moment, but the IES ALC is working with them with a committee to try to assist with writing of the standards and updating them based on industry input. So there's a team working with the FAA now trying to update the standards as their manpower permits it.
I think that's a true statement there, Carl. I think we're seeing more enthusiasm today for enforcing standards, but I am appalled that today for the visual aids on our airport surfaces, there is no there is no enforced requirement for inspecting and for measuring the light output of your fixtures. It is not enforced. And it depends on the airports, as you indicated a few minutes ago, having the interest and the self-respect to have a system that operates for the standards. But the FAA has no certified test equipment to go out and test this. We know Melms does it, and they do it very well. But if anybody else wants to get into testing lights, we have no product certification for that type of equipment. And so we're really, to me, we're in a desperate situation. And we talk about people getting more interested in doing this. But I hope I live long enough to see some of it. Because over here, it's because of Melms, and it's because of airports and people like Carl and so forth that have a real knowledge of what's going on and see the importance of what's going on, that we're having anything done. But the FAA, they're understaffed. They don't spend any time working on standards for going out and measuring the equipment on operating runway surfaces. They may inspect the lights at the time of installation, or that is happening more often now. But the 15 or 20 years after that, you're lucky if you ever see any tests. Maybe a slight exaggeration, but I don't think it's too much. End of
No,
message.
I certainly concur with that. I love your passion. I love your passion. I know this is one of the things that you're fighting for, and I echo. I hope you live much longer than you and you see a full implementation and implementation of inspection and testing by the FAA cert inspectors. And of course, a key element of this is training. Kev and Tony, what's going on in the world of training for low-vis procedures and low-vis operations? You're both muted there.
In what respect do you mean, Robert?
Well, I mean, how are we seeing that? We talk about low-vis operations in our working life, in our training. Is that evolving? Is it developing, keeping pace with the developments of technology?
I'm going to say something now which may be seen or heard as being quite controversial. The main priority I see at the moment with regard to training is an awareness, and it follows up with what Stuart was saying, awareness with regard to compliance. The unfortunate thing about it is that you can have the best lighting facilities in the world, but if they're not maintained to a compliant standard, they're redundant anyway. Whether you're in good visibility or low visibility. So my thoughts are personally that our priority is to ensure that the maintenance training that is provided ensures that the persons carrying out that task are maintaining things to the maximum level. From that, the in-house procedures with regard to LVPs at every airport, they all have slightly different procedures, although have a basic format. The training that they get at their own airfields then should ensure that the lighting that is available and the visual aids that are available are suitable, adequate, and compliant for the job that they're going to have to do under a low visibility situation.
Yeah, I think the regulators, they're the people who've got to move this on and actually take responsibility and make sure that the equipment is up to spec and require it and inspect the records and so on and do all of that. This is very much close to my heart because all of this, TMS, MARMS, all that, I think I can say it's all because I caused a fuss when back in the 1950s, when I was part of a team that was designing the specification of the high intensity taxiway lighting, I actually went to a number of UK airports that were certified for Cat 2, some Cat 3, and looked at the taxiway lighting. At that time was omnidirectional greens, low intensity, and being a good scientist, they told me what the book said. And I said, well, can I go out and measure a few? So I did, and I found that for various reasons, mainly maintenance, but also poor design, you're lucky if you got 10% of what the lighting was supposed to be there. And I said, can I look at the runway center lines? And I found the same. If we say let's just say the center line should be 5,000. I was getting on runways which have been flight tested and by the regulator less than 2 weeks before of less than 200, and yet so there's the regulators have to understand what they're doing, because they thought flight testing they applied, which is really about seeing if the brilliancy switching worked. That seemed to be the main thing they were interested in. It was pretty useless. So they've got to do the right sort of monitoring to see that what is provided. So they do need test equipment being used, and that needs to be certified as Seward was implying. So it's very important. I think it's one of the key areas for them. And I hear what Carl's saying. It'd be good if the regulators really get on the backs of airports and make them comply if they want to retain their license.
Yeah, exactly. We're getting more questions coming in, but we're running 20 minutes over time now. We will address your questions and we will answer them formally on the very good questions, Matt, Mohammed, Nathaniel. We'll get back to you. We'll answer them, and we'll post the answers on our website where we post the video. Thank you for your interest. Thank you for your time. I'd like to thank in particular, of course, Tony, for his magnificent presentation and insightful knowledge and understanding he's provided to us all, which I think is absolutely fantastic. I'd like to thank the panel of Carl, Seward, Tony and Kev for their contributions today, as ever, much appreciated, and their continued support of the safety and compliance in our aviation world. Thank Damon and Felicity, with whom we wouldn't be able to, we wouldn't have this production. As I said, this is the 51st webinar. So, it's an enormous amount of work goes in there. It's all voluntary from the panel and nobody gets paid for this. So I hope you enjoy it. I hope you appreciate it. Please provide the feedback you'll get on the feedback form after this presentation. Let us know what you're looking for in future webinars. The next one will be on the last Tuesday of May, and will be a case study on visual aids, safety and compliance, presented by an airport, actually telling us how they actually do it. And we're going to be featuring a series of these to represent the different environments in which you operate. So I'm looking for volunteer airports in sort of arid, dry conditions, in colder, snowier climates, and in more temperate zones. So and also for large airports and smaller airports, because all of your knowledge and experience is highly relevant to your colleagues, but it's also different because of the environments in which you're operating. So and perhaps even we started providing training on helipads. So perhaps I think we should do a webinar on helipads, safety and compliance. Don't you, Tony? Are you volunteering for that?
I'll think about it. I think
right. So
there is an Annex 14 Volume 2, of course, which is heliport lighting.
yeah. So We will be looking at helipads and I think, I don't know if it's vertiports are a thing of the future. So we'll be, we want to keep you abreast of current developments, knowledge and understanding in the industry. So thank you again. Thank you, audience, for your support. Without you, we wouldn't be here. And thank you, of course, to Tony and the panel and Damon and Felicity for actually making this happen. Thank you, and see you same time next month. Goodbye.
Thank you.